Good morning, everyone. Welcome to the paper presentation of Complexity Theory course. My name is Fahim Ali. So the title of the paper that I'm presenting today is Two-Dimensional Tile Displacement Can Simulate Cellular Automata. Tile displacement is a mechanism in DNA technology using self-assembled DNA origami tile arrays. It involves interaction between individual strands and monomer tiles in solution. An abstract model in this paper they presented an abstract model of tile displacement which is being used for programmable computation from circuits to cellular automata. Every construction varies in different energy uses, space requirements, tile types, and computational power. Tile displacement system are Turing universal and can simulate two-dimensional synchronous block cellular automata using a single tile per transition rule. So here's an example of a DNA structure. So here you can see that there are two backbone of the DNA, and they are being connected with four base pairs. On the right, you can see that it's a mechanism where a single strand invades another DNA strand and replace one strand with itself. You can see that the green strand enters and connect to the white strand and try to remove the red strand. So in the end, the red strand is removed and the green strand connect fully to the white strand. So this paper presents an abstract model called the single assembly tile displacement model. The model defines the behavior of a single tile assembly in a sea of monomer tiles. The model is based on certain assumptions that are experimentally plausible, and the definition of the model is designed to be relatively clean. So there are some aspects of the model. For example, singularity. The concentration of multi-tile assemblies is significantly low, that they do not interact with each other. Monomers binding between two monomer tiles is significantly weak. Stability. Tiles within an assembly, such are those with four neighbors, are firmly attached and will not dissociate. Next is full toehold. So full toehold is a tile that is bound to four neighbors. Four neighbors will be displaced by a tile that forms a toehold on each of the four sides. So energetics. The tile displacement reaction must be either energetically neutral or energetically downhill. And close open toeholds. So and specific toehold on a specific tile is closed if the corresponding toehold on the neighboring tile has the same bond type. Um, while we can say that it is open if there is no bond between the tiles. Unreliability. Unreliability is in tile displacement system. If there is an energetically neutral or downhill replacement tile displacement at any point that does not create at least one new toehold with each neighboring tile, the simulation is deemed is can be called unreliable. So here you can see that this is a single standard DNA, and this single standard DNA forms a structure like this with multiple other single standard DNA, and they bond to each other like this, and these bonds are called toeholds. So for every side there are two toeholds. Here you can see that this style also can be represented like this, and this tile is connected to other tiles, to other neighboring tiles. And when the tile has five bonds, like for example here you can see that in the left side there's there's another bond, and it connects to five different areas of the neighboring tiles. It is called downhill. And if there is less than four bonds, for example here you can see that there's three bonds, we call it the uphill. Next we will look at some simulation. So the first simulation is the wire. So in so the every tile displacement each reaction in tile displacement is neutral regarding bond energy, and the tile displacement rate is more or less the same rate, and the expected time that is been calculated for signal transmission for a length of the wire length of n is that it is n square. So here's a presentation of a wire. So for this we are using four tiles. The first two are the supporting tiles of top and bottom, and this is the wire tiles, and this is the single tile. So the main goal is to replace this wire tile with the single tile, and here you can see that the single tile has a different code, it's X, which we want to transmit from left to right. So here you can see that the first tile is a single tile, and I want to replace the second tile with the second white tile with the another single tile. So the single tile here, you can see that the connection of the bond is different from the wires. Um, and when this single tile comes to here, it replaces this white tile and position itself here. Here you can see that in the left and the right, the white tile has been removed, and in his position, the single tile has been replaced. But there's a problem in this construction, because this wire tile wire tile has not been removed from the monomer solution. It can come back here and also replace the single tile. So and this will go in the reverse way, and it will not be fruitful for the signal to propagate. So to tackle this problem, there is another construction, which is the irreversible tile, irreversible wire. So here the we use downhill bond energy to stop the reverse process, and here the the expected time of the signal transmission is big O of n, where n is the length of the wire. So here you can see that the difference between the reversible tiles and the irreversible tiles is here in the signal tile. They added extra B here, B code here in the irreversible tile. By doing this, when this tile replaces the wire tile, it forms two bond. Here you can see that it has two bond, and it connects to the B and the X, and for this reason it has five bonds now, and the wire has four bonds, and now it cannot replace this um, single tile. So yeah, so this is the wire irreversible. Next is wire cross. So here you can see that there are two signals coming from the left and from the bottom, and they connect together in the middle. So here for this construction, the goal is to propagate the bottom signal to the top signal and the left signal to the right signal. So for this construction, we are using eight different tiles, and the mechanism is that when these two tiles reach in the these two signals reach in the middle, this middle tile replaced by a gate tile. This is a different kind of tile. It's called a gate tile, and this gate tile converts this X signal into a Z signal. Here you can see that Z signal, and this W signal, which is coming from the bottom, converts to a Y signal. And when it replaces here, after that, you can see that when it replaces here, it removes the wire tile. W single tile can be placed here, and X signal tile can be placed here, because it has the four bonds which can connect to this gate tile. So this is how wire cross can be constructed. But the problem is that this is also reversible. And to tackle this problem, so here is the construction for irreversible wire cross. So here you can see that the that to to prevent the reversible process, there is a downhill tile which is been using which has been used for the left signal and the bottom signal. Here in the left signal, you can see that they formed a five bond, but there is a problem. If in any case for example, in here you can see that if the left signal comes first and the down signal is yet to come to the middle tile, the gate tile can be formed without the signal tile reaching the middle tile. For example, here you can see that the bottom tile has not been yet to reach this middle tile, but because of this left tile, the gate tile can come here and form the four bond to hold in this position. So this is a problem, and to tackle this problem, there is another solution, which is using latches. So signal zero has a another tile which is latch zero. Signal one has another tile which is latch one. And here you can see that when the signal is propagating from left to right, the latch signal, here is the latch signal, and here is the signal zero. This latch signal connects to the middle of the tiles, these two tiles, and the signal tile replace this wire tile. So the latch tile replaces the signal tiles, and the single tiles replace the white tiles. So here you can see that in the latch tile has replaced here. So it is also same for the single one, and there's also a latch one tile here which can be replaced, which will replace the single one tile. So next we will look at some gates. So here we can we'll observe XOR gate. So for XOR gate, we will need we'll need 9 different tiles. So actually it is four, 8 different tiles, and here you can see that this process here. So for example, there's a zero signal and there's a one signal here, and both this signal will come together and meet here, and after that uh, there will be a OR signal with OR operation here with the 0 and 1, and we know that for 0 and 1 in OR gate we will get 1 in return. So here for the XOR we have 4 different tiles. So these are if the input, this tile is for if the input is 0 0, and this for is if the input is 0 1, this is 1 1 0, and this is 1 1. So here you can see that 0 and 1 is coming, and when it reaches this two position, uh, depending on these two position and these two signal, these two tiles, uh, the get tile will be located. So here you can see that you have a 0 and a 1. Because of this 0 and 1, we'll have to bond a tile here and here. So which one is that? Which is this one, this tile. So you can see that this tile has been replaced here, and in this tile we have the 1 and 1 signal. See, so this middle tile has been replaced by this tile, and it positioned here. After that, because of this particular tile, they in the top tiles and the right tiles will be replaced by signal 1. Here only signal 1 tile can be replaced in this well because of this gate tile. So this is how XOR gate works in the tile displacement automation. Here is another circuit. This is a very popular circuit. Um, this is called systolic array of XOR gates. It has 18 inputs. So when the inputs are given like this, the bottom inputs are all zeros, and the top inputs and the left inputs are all zero. Only one has the signal one. So when we simulate this circuit, we get a pattern like this, and this pattern is called a Sierpinski triangle. So this triangle is formed because of these two signals, the result of these two signals. So what if we try to simulate this same thing in the cellular cellular automation? So here you can see that this same thing has been done with the cellular automation. Um, so this for this automation they call it a one-dimensional block cellular automata, and there are the inputs are from fixed given alphabets, which is A, and if the size of A is n, then we will need total number of 2 plus 2n plus n square tiles. For example, here you can see that they have used two alphabets. So two alphabets, and so the n is 2. Because of that, they are using 10 tiles here. They're using 10 tiles. So each time step, the entire array is synchronously updated by applying. So for every time step, they're using this rule to update the next tile. Mm, and for the same array, the cellular automata approximate computes roughly 10 times more gates. So the nth synchronous update of the 1D block cellular automata will be encoded in nth diagonal of the tile array. Similar to the gate tiles in the circuit construction, the displacement must match all four open to hold position, else it will be energetically unfavorable. This can only happen when both the tile to the left and the tile below have already updated, thus ensuring that the information is biased. Computed information is based on the correct information from the preceding diagonal. So here you can see that It is same as the previous circuit, previous circuit here. So that inputs are in the left and bottom, here also the left and the bottom, and these are the inputs, these are the blanks, and this diagonal is being replaced based on this tile and this tile diagonally. The, this this two tile is responsible for the tile here. So if we try to simulate this automation, it creates the same same pattern as it is presented in this circuit. So the implementation for feed-forward circuit and one-dimensional cellular automata computes in linear time using reversible toe-hold formation. With respect to the size of the initial array and the tile set, the construction can solve p-time problems. Tile displacement is so this time displacement construction is p space complete problems. So yeah, that's the end of my presentation. Thank you.